Good afternoon, everyone. First of all, thank you very much for your attendance. Here is our distinguished lecturer, Wenkiri. And Wenkiri is a Regent Professor and John Imali Junior Chair at Georgia Tech. And his research interests include systems and network security, model analysis, applied cryptography, and machine learning. He received his PhD in computer science from Columbia University, and he's a ACM fellow and IEEE fellow. So today's talk title is Privacy and Reliability Issues of AI Systems. And then, yeah, please go ahead.
Thank you. Yep. Thank you all for coming. So it's a pleasure to be here. So I'm going to touch upon some issues of AI and AI in AI system. I'm sure there are many issues that people can talk about. So I will start with saying that, I mean, obviously, everybody now, when we meet, we talk about AI and all that. So I think some of the questions basically say, hey, what can AI do for us? How are we sure they're doing the right thing? So to me, we can debate all day long, for example, whether AI system can actually really have the same intelligence as human and then can reason like humans. So basically, all of those things, to me, is somewhat philosophical in the sense that how to define intelligence, how to define reasoning. I'm going to touch upon some of these debates towards the end of my talk. But to me, I'm more focusing, because I'm a security guy, I'm more focusing on the reliability and privacy, ethics, safety, and security issues of AI. So to me, you can say at a high level, I can think of two orthogonal classes of AI applications. One, we don't really care about reliability and safety and all that kind of messy stuff. For example, if you put your AI system to the sky, say, tell me where there's a new star. And in that case, I'm sure most of the time it makes mistakes, but every now and then it finds, here's a new star. Awesome. Meaning that for that kind of application, we call it exploratory applications. Yeah, I mean, it takes, we can spend all our time to analyze the outputs, and even though it makes mistakes, that's okay. But then I think the danger is that people think, it's awesome, look at that, you can find a new star. Okay, then they turn around, make a quantum leap in terms of thinking and say, now let me apply AI to some critical applications. I think there's a quantum leap that we should be really careful about, meaning that you cannot take the AI as a black box to think that it can do anything you want and apply to a critical application. So for those who really have to think about, really can it do things in a reliable way, you say, how do you measure it? Well, how about you should do at least as well as the current system. You cannot say you replace current system with AI-based system, but then it performs worse. Then what's the point, right? The baseline should be, it should perform with the same reliability as the current system. That to me a baseline. Then you say, well, because AI, I can do a little bit more, I can automate, I can be faster. Okay, that's add-on. But you cannot lose the basis. So that's what I'm trying to say, is that how do you guarantee that? That's super hard, actually. Because again, if you treat AI as a black box, you don't even know it actually can perform the same thing as the current system. Okay. Anyway, so I'm give you, the reason that I think this kind of talk would be suitable for IST is that my experiences with my work in the past, 5-10 years, is that I realized that we as technical people sometimes will forget about some of the ethical privacy policy aspects until it's almost too late. So a classic example is actually using computer vision to do face recognition. I'm sure you have heard of this complaint about all these face-based systems are being biased, right? They're super accurate in identifying, let's say, white males, but not everybody else. It's, these guys are biased. You cannot blame technical people. You can blame on training data. When they train the system, they use predominantly white male images. Okay, but then pushback that shouldn't they know? They didn't know, because most of the time when you sit in a classroom, you are not taught about all these considerations. You just talk about technically, how do I recognize that face? Most of the time you don't talk about biases. So So actually, my point is it has a lot of consequence, right? People actually have now starting to basically either don't trust these systems, or they think that the technical people, they have no regard of human privacy or ethical constraints. So let me talk about some of the work that I do in the past that actually force us to think about some of these issues. For example, face-based authentication, right? So imagine you can use your face to say, I'm Wenqi Li, I can walk into a building, there's a camera that knows who I am. Except that a lot of these systems, in particular the example I gave, where you walk into a building, the camera captures your face and know that who you are. Normally that means a server stores something about your face. Okay, so think about what the server is storing. The state-of-the-art standard is that they store the clear picture of your face. So whether you like it or not, I mean, most people will think, well, why do you have to store my face? Clear text. It's almost like you log into a server, the server stores a clear text or password. You like that? Of course not. We want to say, hey, the server should only store the hash of my password. Right? So that even if the server is compromised, for them to know my password, they have to do the password cracking. Good luck. Right? Of course, provided that you have a strong password. Same thing here is that, can we actually say that the server stores your face? Even the server is compromised, they cannot know who you are or how you look like. Now, of course, you say, why can't I use my iPhone thing? Yeah, the thing is, that's pretty secure actually. All your Face ID actually stored in a secure enclave, which is completely separated from your main processor, and the embedded system completely separated from iOS. Which means even if your iPhone is compromised, physically obtained, nobody actually can extract your face data. All good. But the point is that, of course, in that case, server, the Apple doesn't know who you are, how you look like. Awesome, except the things that you can do a lot of social engineering. For example, you say, my former postdoc Hong Hu said, I'm Hong, and I know Hong's, let's say, modest maiden name. What is the information? And I can convince Apple to actually accept my new phone. In that case, Face ID doesn't really help. I can basically assume the personality. So the point is that really there's a lot of benefit of having your face data in the server, in the privacy preserving way, so that you new enrollment, lost phone, new phone can take care of that. So how do you do this? Why can't you take your face picture and hash it, and store the hash of your face? Same as storing the hash of your password, right? Well, not so fast. It's almost like I said, Home, don't move, freeze, right? I take a picture twice, I guarantee the image will not be the same. Just the lighting, the physics, or maybe you blink your eyes, whatever. Or the wind's blowing a certain way, your hair moved, whatever. So the point is you cannot guarantee that if I hash your image, that your face will guarantee will match the hash of what I store. It cannot. But fortunately, the cryptographers had thought about this. This is whole sub-area called fuzzy extractor. It actually specifically was designed to handle biometric data. Can be face data, can be fingerprint, can be voice, in the sense that they extract from your face data, let's say biometric data, some bits from the data. Let's say call it some strings. They extract enough strings, let's say n separate strings from, of course, key features of your face, let's say, and guarantee that same person is at home in different contexts, K out of n would match. What's K, what's n? Yeah, literally depends on a lot of empirical study. The point is that if K out of n match, almost guarantee the same person. We almost have very, very small chance of you actually misidentify a person. So that's the first extractor that the cryptographers have done. So that's what we use. So basically, I'm going to tell you quickly how we achieve privacy preserving biometric or face-based authentication with the server involved, meaning the server stores something about a face in a secure and privacy preserving way. So here's a quick walkthrough. Let's say that you're this person, you take a picture, right? It can be your phone, can be your computer, can be a camera, whatever, as long as a smart client can do some local processing. So local processing is happening here is that you record the filter, like filter out some noise. Of course, you power your face through some deep learning based model. In this case, you can get a model from FaceNet. It's good enough that actually the baseline model is so good that all needs to extract some features of your face and then fine tune some of the parameters. Boom, then you have an embedding of your face. Then basically then we extract some signal, basically extract what I call the fuzzy extractor, extract some strings from this your film model, and then we do a noise reduction. I'm going to explain this. So basically, yeah, so that's that. Right? Noise reduction means that, like I said, just even though you do a fuzzy extractor, you still should worry about the certain movements or some, how to put it, the bits that you extract. Not every single bit should be counted because they're more likely to be, compromised by some noise, some movement, some environment thing. So you want to have some mask here. We call it noise reduction to say I only care about, let's say, these 2 bits. The rest I can mask. And for different string, you can mask different parts of it. So you can kind of accommodate for different features. Extract. You allow some errors when you extract those features from your face. Anyway. That's the main idea, that you basically say, okay, I only care about certain bits, and then basically you apply the mask to the string that you extract from the face. The result is what we call now. We say that's the encryption keys that you use. So again, we walk through from here to extracting the encryption key based on the face data. Then what? Then we basically encrypt some secret using those keys extracted from your face, and store the basically what we call locker, basically encrypted secret, on the server, and also the hash of that secret on the server. So at this point, you should be convinced that this is very similar to hash your password, right? In this case, we hash this. In this case, the hash essentially is the encrypted secret, but we also put the hash of the secret so that for authentication, and we're going to talk about that. So far, so good. Okay, so we're going to walk through then. That's enrollment. Then walk through the authentication. That you make sure that you really understand what we're talking about. So authentication. Let's say now this time around, that's the enrollment, right? The authentication means that you show your face anywhere that can capture your face. That has a smart device that can do some client-side computation. Walk through the exact same thing. Get your picture, do the quality filter, deep learning, get the embedding, extract some strings, do some noise filtering, like meaning that that basically do some masking of the bits, and then you, let's say, derive the key. So then at this point, the server, you got the key, right? So then the server essentially, to authenticate you, the server sends the hash of sends the mask. Or also the locker. Say, hey, here's the locker. That's the encrypted secret. And then basically the client the client's job, to authenticate, the job is to basically be able to decrypt the locker sent from the server. How so? Well, because the client just extracted the keys from the face. You should be able to, if same person, that means you should be able to extract the same keys. That means you should be able to decrypt the encrypted secret sent by the server, yeah? And then the client would then say, okay, I decrypt the secret. You don't send the secret, of course, in clear text back to the server. Normally that's a security 101. You hash that secret, send back to the server. Say, yeah, I had a secret. Here's a hash. And the server just compare that hash that sent from the client with the hash that it stores. And the match, then the same person. Simple, right? Again, everything that we use here actually is well known. So why do people not use it? I don't know. I mean, it's like I said, this technical people never thought about privacy is a concern. To me, it's like kind of crazy. But anyway, so that's that. And then there's some assumption here that we say, it's like we basically say, hey, look, even if a server is being compromised, is okay, and the attacker, even to capture the database. What can do? Breaking the hash is not easy. One-way function, right? Guessing the key is hard as well. Do you have a question? Okay, yeah. So So then basically, I mean, the key thing they want to claim is that whatever server stores, like the encrypted hash, encrypted secret itself, of course, the key is derived from your face. But by looking at the encrypted secret, you cannot guess what the person looked like. You can only do brute force. You can say, oh, I look at the encrypted secret. I can then reverse and figure out how the person looked like. No, the connection is not there. So that's why we claim that it's privacy preserving that way. Okay. So yeah, and then yep. So basically, this standard stuff. Yeah, we basically okay. So before I jump to that, some interesting results. People always ask, what if you have identical twin? Yep, that we said no, nothing we can do about that one. And then you say, how likely that I can just randomly guess a face? We tried experiments. I think our results that you can probably you try 6 million faces, you can probably get one. So 1 out of 6 million, that's pretty good, I think. Now entropy wise, probably like 20-some bits. Is it better than a very, very super strong password? No, probably not. But in this case, that's the thing about biometric, right? You don't have to remember anything. Just show up. Right? So that's the convenience thing. So that's the okay. All right. So that's privacy preserving biometric authentication. Now let's move on to surveillance. So surveillance means that you just walk around on the street corner, you're being taken a video. Why? There's a safety. I mean, the safety public safety thing, like to see whether there's most wanted persons there. Awesome, right? On the other hand, just because you are there, or you are there, basically these are basically stored in the clear in the video, somewhere in the police the station or whatever, or the airports or whatever the vendor, right? The street vendor. So the point is that there's a privacy concern as far as I know, in the sense that why do you want people to know that you are there at that time? Right? I mean, just in case if somebody look at some data, say, do I see a most wanted person there? Oh, by the way, I also know this person. I happen to know him. He was there. That was interesting. You probably didn't want to do that, right? I mean, there's a historical story many years ago, like more than 10 years ago in New Jersey. Either database was leaked or some reason people was able to obtain some of the cameras on the highway that who maybe passing the token booth, and then it caused quite a few how to put it. It resulted in a few divorce cases. People say, I didn't know they were there with that woman, whatever. So my point is that you just are unintended consequences you may not want. Okay. So the question is that can we have both public safety and privacy, right? So the current thing is that you basically do this, right? You basically take a face, like I said, you extract the face from your video. Our computer vision expert will tell you that's super easy to extract face from faces out of video, and then you do a search in a database, and then there's a matches. Oh, that's a person. I want to basically, whatever. Oh, so the thing is this, right? So this Clearview AI, you should search for it. Basically, Clearview AI is super aggressive. They basically crawl the web. Basically, the chances are they have your face. They know who you are. What can you do about it? I don't know. It's too late. Probably go back to ask them to delete your face. But that's the current scheme is that yes, public safety awesome, but then privacy is out of window. So basically, my point is, can we have both, right? So turns out also actually pretty simple from math. Well, we did have a paper that actually my crypto colleagues help us to do some proof. I'm not going to go into that, but basically the principles are pretty simple actually. Like I said, you can detect face. So what we can do is that actually you can actually essentially try to encrypt the query. The high level point is that you can actually encrypt your face. When do a search, the goal we want to achieve is that you encrypt your face, do a search over the database, so the database server doesn't know who's being searched for. Okay, and also we don't want the client, in this case, let's say this person who actually control the camera, we also don't want the person to know. I mean, so we all, I'll put a step back to say, I want this person and the server's yes or no, meaning that it's a match or no match. The server doesn't know who's being searched. That's super important. And for the client side here, all the client side should learn is that match or no? Meaning there's no such thing called partial match. Meaning, hey, maybe this guy's brother was on a database kind of thing. So basically try to protect as much information possible, meaning that it's almost like least privilege kind of a principle of security. If you don't need to know, I don't want you to know. I only want you to know things that you have absolutely must know. Okay, so that's a security principle. Like I said, you encrypt this query, search over database, and then when the result is yes, then you can locally decrypt and actually know that. So give you, so the search also is encrypted. How to put it? We search over the encrypted data, meaning the client side, the query is encrypted, database is encrypted. Using all these standard stuff like fully homomorphic encryption, secure two-party computation. I'm going to briefly talk about this, right? So fully homomorphic encryption is like this. Let's say I do 1 + 2 = 3. Awesome. Let's say what fully homomorphic encryption means. Means that I encrypt 1, encrypt 2, send to the calculator, say add this number together. The calculator says, okay, here's the result. The result is encrypted 3. Meaning that the operator can operate on encrypted data input and give you the correct encrypted output. Okay, so in this case, you just imagine the operator itself doesn't know what the input is, but still do the correct computation. Okay, so yeah, so another thing that we talk about is that I think one thing we realize is that you don't want it. Let's say if we do a search, it's not exactly matching this one, but kind of. You don't want to do that because, like I said, you don't want people to, I learned, this guy's brother or cousin is on the database. So what we did is some very simple techniques. Let's say we put each database record with a label. And then we then basically have mask, meaning that have multiple subsamples of the same face data. And then when you match, you need to match, let's say k out of n samples. And only then the label will be revealed, meaning that we basically do a secret sharing of the label across multiple samples of each data. So that if you only match part of it without k, meaning that if you match up to k - 1, we tell you no match. We don't tell you match 1 or k - 1 or 0. But when you match k or above, then it's match. Then we tell you the label. So that way, the query, the client who sends the query only knows yes or no, cannot know partial. So that's a privacy thing that we consider. Okay, so and then some of the details here. Basically, like I said, we subsample, and then basically the server comes up with a key and a mask, and then already locally compute the input, and then sends via two-party computation, so that the client basically sends the mask to the client to say, hey, do this. The server sends the key and the mask to the client. The client will compute its own encrypted version based on the key and the mask, and then we then basically have a two-party computation. Yes.
So right now you assume the client only needs to know yes or no, right?
Yes.
I imagine in certain situations the client might need to know which person it is.
Yeah, it is. It will. The label tell you. When you match, the label tell you that's the name of the person. So the point is that let's say with 3 samples. Well, so let's say we have 3 samples, meaning that each face we create 3 subsamples, and then you essentially distribute the label. Let's say your name, doing secret sharing into 3 pieces. We say that you have to match 2 out of 3 to reconstruct the name. So which means that if you match 2 out of 3, then you know who you match. But you only match one of them, tells you 0. You don't know you match parts. For example, I matched this person's eyebrows. No, you don't even know that.
So will the server know that information as well?
No, server doesn't know. So here's the thing. Basically, the comparison is in a two-party computation, secure two-party computation. So basically, first of all, two-party computation means that you don't know the input, right? So basically, you do the comparison based on fully homomorphic encryption, but you don't know exactly the input value. Yeah. So, any question? Yeah. So, but anyway, yeah. So basically, the details in the paper, like I said, a lot of that I don't even understand. So basically, that's what normally so here the side check is that I normally tell my student, if anything touch with crypto, first of all, you cannot invent your crypto. Normally, if you do that, you're normally wrong. Second of all, even you think you're doing the right thing, yeah, think twice. So that's why, in principle, I always ask my crypto colleagues, here's what we're doing. What do you think? If they say go away, that means we're doing it right, too simple, they don't even want to bother. If they say, oh, let me take a look, that means they normally can contribute. In this case, they actually contribute to a lot of proofs. Anyway, so I don't want to bore you with that because I don't fully understand what the hell they're doing. But anyway, I just assume they're correct. These are world-class cryptographers. Okay. Anyway, so yeah. So then we'll switch topic. So I was recently at Singapore at a security event. I had a pleasure to see Taylor Swift here. Do you believe Taylor Swift will show up in Singapore at a security event?
No.
Of course not. Obviously not. So basically, it's a real-time deepfake. That was so impressive. Basically, what happened? Yeah, actually, the real person is this. You look at the same clothes, right? The person you show it basically is like the real-time deepfake is so impressive. Basically, you walk in the booth. The booth has a camera mounting there, and you show up. They're supposed to show your face or image right there on the screen in real time. But if let's say you step on here, this particular spot, you basically immediately in real time impose Taylor Swift on you, or or Brad Pitt, whatever. Yeah. Okay, so basically real time though. I was like, wow, this is so impressive. So the first time I saw real time deepfake in person, super impressive. So that's why my friend took a picture of herself. Anyway, so it's like, all right. So the point is that, but deepfake really is everywhere. I mean, whether they like it or not. It can be all kind of things. It can be like for a joke, can be a propaganda thing, can be for entertainment. Yeah, sure. I mean, you can do kind of movie stuff there. But even for trusted, trusted one of men is that our vision expert, computer vision would tell me that correct that. Even you take a picture of this person, right? Then you can construct a vision model so accurate. Then you can look at that. You can basically say, oh, I can actually know, based on the clothes that she's wearing, if she walks, see the kind of movement you will see. I mean, it's like so realistic. It's amazing. So it's almost like I'm fine with AI taking over and Hollywood just go away. Who needs them? We all can produce our own movies as realistic as we want. Awesome. So I'm no sympathy for Hollywood. Anyway, so seriously, but the point is that the deepfake that really works, is actually technically very sophisticated. We actually have an ACM survey paper that published 2 years ago. They cited 700 times. That means really people are actually really interested in this thing. But again, the survey paper written by my postdoc. I don't know most of the stuff, but pretty deep stuff. But the conclusion here, the high level thing is that really a lot of models, meaning that the deepfake, they're really using the most advanced AI models with computer vision, and sometimes multiple these models combined, right? So, all these, it's like, wow. So give you the simplest example, right? Let's say encoder, decoder, that's like the classic, most basic model, right? So basically encode, you basically say, people talk about embedding. Basically, embedding is the internal representation of your input. For example, say face. My embedding would be the key features of a face, not every single pixel, right? Only I care about how do I embed or how do I represent the input. In this case, the input of your face, my embedding would be the key features, not the edges and the outlines of objects kind of thing. And then decoder basically say, hey, based on the embedding, how do I redraw, let's say, how do I redraw the face? Or how do I recognize the same person? Again, based on the embedding, how to interpret embedding. Let's say embedding, in this case, the embedding is the key features. Then I know how to draw a face based on the embedding. Do I care about pixel here? Probably not. If it's not captured, that means it's, just paint it whatever color you want. No, I'm joking. But saying the same thing with face recognition. It's the same, similar embedding, meaning same key features, of course, same person. All right, so that's how it works. Okay, so how is it being used? So for example, but the things that you can mess with the embedding, then you can interpret, then the decoder doesn't know. That has been messed with. So you could draw a different person. That's exactly the simplest deep learning deepfake would do. For example, you say, okay, the normal embedding, I can actually train the model, I can actually know how to draw a face or recognize recognize the same person. But the thing is this, right? If I want to basically do the deepfake, I just mess with certain part of the embedding. So then when the decoder interpret the embedding and it will draw to a different person. That's in a high level, that's the basic understanding of how deepfake works. Okay, so yeah, so that's that. So then, so how do you detect them? Yeah, sure. There's some, there's certain thing you can do. For example, there's some certain classic forensic, meaning some of the parts that are being generated, or there's some signatures there, or there's something that I don't know. Maybe some of the features here are not natural, whatever, because the way it's generated is not, And then some of these are completely the kind of default, fallback would be you detect anomaly. Say, hey, doesn't look like a normal person, whatever. So you can do a lot of that. So not totally surprising that people attempt to all kind of ways to detect deepfake. Yeah. So I mean, to some degree, depending on how sophisticated deepfake is. Okay. For example, this face. You think this is a real person? It's not. It's a very famous face, but generated by the GAN model. Looks real, right? Completely. Like I said, just right now look at a static picture, you cannot assume it's a real person from a real person or not, right? Because really the computer vision and has become so good that it can generate very realistic looking face. But the thing is this, you can actually, if you know the GAN model that it uses, you actually can also derive some signatures. Why? Because our vision expert will tell you there's some biases in terms of how you actually do signal processing, how to draw certain things. There's the signature that you can use. This thing must be generated by this GAN because there's some some part of the image or pixels had this kind of signature because of the image processing or vision algorithm they use. Okay, so in this case, for example, right, people derive all these signatures of all these well-known models. So the point is that if I analyze the image, I find those signatures, more likely than not, that was generated by some of those models. Okay, so it's one way of detecting generated image. For example, the picture that I showed previously, even this person is not in training data, doesn't matter. If when you analyze the pixels, it actually had those signatures, you kind of know, I know it probably generated by that model. Are we all good? Of course not, right? We could keep seeing deepfake. So the point is, for example, right? You say, I know they're using signature-based stuff. Okay, I'm going to mess with it. How? Well, I mean, I'm sure most of you have heard of this story multiple times now about, let's say there's a object detection system that, say, hey, that's a cat. And somebody flip a few pixels. All of a sudden the system, that's a dog. I'm sure you heard of that, right? Same thing here. If I know that, hey, you are looking for signatures of this kind of model, all I need to do is basically mess with some pixels. And then we'll defeat a signature. Basically, if I know the signature, I can actually modify my image to to basically mask those signatures. Okay? The thing is, another thing about, I'm getting a sidetrack of my talk here, is that that's one of the areas in AI that really bothers me a lot, is that there's lack of so-called input filtering from a system security point of view. Because the pixel that you mess with here, let's say you add a pixel here, human eyes, do you see the difference? You don't. Same problem that people say, hey, yeah, somebody flip a few pixels. I can still see that's a cat. Why the AI system thinks a dog? Here's why. That's the problem with deep learning. Classical machine learning say we need to do feature engineering. You know exactly, we basically just describe the problem or properties of problem to AI system before you train it. Deep learning say, too much work, no need for feature engineering to give a lot of data. Well, the consequence is that, at least for image processing, the AI system thinks every single pixel is the same. Every single pixel is the same feature. It doesn't know that, that feature is ignored because that's not human face anyway. Or it's not the most key features of the eyes and nose. No. AI system does not know that. Why? Because it said no need to do feature engineering. Okay, so that's why when you flip a few pixels, you're actually flipping a pixel that actually not consequential. You say, then why is input filtering useful to you? Here's why. Like I said earlier, that's why it's just so hard for people to wrap their minds around how they make sure the AI system have a chance to work better or work reliably. First of all, you say, my AI system replaces application X. I should ask you, what is application X doing? Let's say, oh, my AI system is do face recognition. Okay, like what? I'm going to replace human eyes. All right, good starting point. Then you should focus on the pixels that human eyes care about. Okay, so that if attacker manipulate those pixels, human eyes say, yeah, that's been manipulated. Now I know why. The AI system will actually see something different, right? Instead, you say, no, I accept all possible pixels, even the pixels that human eyes will not be able to process. Then you actually essentially open up your attack surface too wide to things that you should not have considered in the first place. Okay, another classic example that I normally want to use for lack of input filtering is the famous attack on injecting quote-unquote voice command to Alexa. In this case, even a human person will not be able to hear the so-called input command to the Alexa. Alexa says, "Oh, the human user tells me to open the door, so open the door." Again, that's a classic failure of input filtering. Why? You should ask, what's Alexa supposed to be doing? Hearing human voice. Okay. There are certain sounds human can make, there are certain sounds human cannot make. The attack in this case actually were injecting voice the human vocal cord cannot possibly make. In fact, they couldn't even hear it. Yes?
So that sounds like a very simple idea to apply. Did you try this idea on this image?
Yeah, so actually, we have people actually in kind of a vision AI expert, they compress the image. When you compress, this attack will go away. Because that's a very minor amount of pixel that will not be useful anyway. There are a lot of people are starting to focus on all kind of input filtering, but not in a systematic way. I mean, like the AI people, that's why I kept saying the AI people, the system security people, like they are, I don't know. The AI people tend to say, who cares? Give me enough bad examples. Eventually they will learn to ignore those. Yeah, really, give me a break. It's like you're doing hard work. Well, why do you have to make it so hard? Whereas if you do input filtering, it was so much easier. Why do you not do that? But anyway, that's a debate that I can go on forever. So, all right, yes?
Do you need to know the signature for this? Can you just do like random white noise and it will start?
Yeah, but the random white noise, your chance of masking the specific signature will be also random, right? Yeah, I can go on forever for input filtering, least privilege, all that other kind of thing. But AI people, they're not security people, so they, whatever. I think they still believe in, I need big data, big computer, eventually, really. Anyway, so, all right, so this arms race, like I said, so my point is this arms race, how do I get around it? I do have a good solution, but, it's almost already there, meaning that if you have a small camera that has a chips, has a camera-specific private key, simple. Just hash the image, hash the video, sign it, put it in a blockchain. Game over. Nobody can deepfake it. Why? You can always verify that. You cannot deepfake it. Because it has to be from a camera that people know. Let's say I'm a camera manufacturer. I manufacture a camera. I publish the public key of that camera. Every camera will be different. Guarantees that when the camera shoots the video or picture, it will sign it using its unique private key. Right? Sign the hash, put it in blockchain. If somebody ever question whether that video or picture was produced by a real camera, yeah, to verify it. The public key is already published. There's no fake. You cannot fake. If that still can be fake, then the whole trusted computing platform just collapse. That's the only thing we can count on, right? Yes? Hardware-based trusted computing. Okay? Actually, I think there's a camera that already do that. That can already do that. Why they're not doing it? I don't know. That's IST people should talk to business people. Say why? Why is it too expensive? Whatever. But then the things that, in the meantime, we can do some contextual thing, like in particular for live authentication. You can basically make some task. For example, here's a postdoc that wrote a survey paper. They say, hey, let's say you do different authentication, but you don't know whether the person authenticating himself in live situation is a real person or not. You can ask him to do a number of things. For example, hey, hold a pencil. You say, wow, I haven't done this before, so I don't know. I can compute and generate it like in real time. But again, these are arms. I'm talking about arms race, right? Maybe in the future, the supercomputer, enough knowledge, it can do this. But the thing right now, you ask for all kind of real-time challenges is clueless. It couldn't generate. Like this is my favorite example. Hey, point your camera to your body. I don't have a body, man. I'm fake. So basically, it's completely. You see what I'm saying? So right now, you can still do this kind of thing, but like I said, don't bet on it for too long, because like I said, with the supercomputing power behind it or enough training examples, you may be able to catch up with a lot of that. But anyway, so that's arms race. Like I said, smart camera, sign the hash, put a blockchain. That's my solution. Okay, maybe in 5 years we can do it. All right. So my one last piece. I wouldn't take too long either. So basically, the question is, can LLM reason? Right? Can do reasoning. So people have different debates and all that. So we say, yeah, different kind of opinions of that. So basically, yeah. So this agreement is that there's actually no definition of reasoning in terms of natural language, right? The language generator basically based on probability. Most basically saying what's the most probable next token in the context of what you're asking, right? Is it rigorous reasoning? No, it's not formal logic the way that we want. So, but again, you say, well, I have different definition of reasoning. Who said reasoning has to be formal logic? Okay, here you go. That's why we have this kind of debate. And also things. Okay, then the question of can LLM reason? Well, don't even know how LLM works. So that's like, okay, you're asking a question that's too hard for us to answer now. So then, so then we say, okay, our approach is that let's start with something very, very simple. Let's start with some very basic, mechanical, logical question to see whether we can make LLM follow that. The point is that if LLM cannot do that, there's no way they can do any reasoning. Right? For example, you say, hey, I want to see whether LLM can do some formal reasoning. Well, start with something super basic to see whether it can do it. If not, then there's no way it can do more complex stuff. That's where we are. So in particular, we're doing self-solving, right? So basically, well, let me before I jump into that, self-solving, I'm going to explain that, right? Basically, very simple Boolean logic reasoning. Like say A and not B, can this ever be true? Basic stuff. If you cannot even do that, there's no way you can say, oh, LLM all of a sudden can prove some correctness of program. Really, no way, right? So you understand my thinking here, right? So then we say, okay, now, of course, we have the experience of asking ChatGPT, how do you do this? Normally, a lot of time we give wrong answer, but if you ask him to, hey, give me train of thoughts, train of thought meaning that you give me all the intermediate steps, you actually had better chance of succeeding. For example, right, here's a hey, have this, so basically say, hey, you ask, hey, what's the 23 apples and this and then if I ask the language model to give you train of thought, it actually tells you step by step, not just answer. Without that, you tell you answer is 9. But if you ask for train of thought, if we actually do the step by step, processing and then give you those steps. So I think a lot of there's a lot more research now in train of thought in the last couple of years, which is I think the right direction to push. Basically, you then can also help you do better problem engineering or help the language model to improve itself. And also I think it's more, how to put it, I think train of thought is closer to reasoning, that the kind of reasoning that we want it to see, step by step, okay, linear kind of reasoning. So self-solving, right? So very, very standard, basic computer science kind of a problem. Like I said, this is the most basic logical reasoning framework that we can think of in computer science. And the things that if ChatGPT cannot do this, or LM cannot do this, then there's no way it can do anything else that we care about in software. So basically say, hey, we call 3 set because only each class has 3 variables. And the question is that, can this formula be satisfied by assigning true and false to each of these variables? Meaning that is there a assignment to these variables that this 3 set formula is satisfied, meaning that it's true. Or you say, I tried all of them, I couldn't find them, that's unset, meaning this cannot be true. So the typical solution for using train of thought to solve this, which we can program the ChatGPT to do this, basically say, hey, you're basically doing essentially, let me see here. Yeah, you're basically doing essentially follow train of thought. You're basically doing search and then backtracking. For example, you say, hey, assume x2 is true, assume x1 is true, then you kind of derived, okay, then x4 can be false, and then x3 can be false, can be true, and then you say there's a conflict, meaning that this all of a sudden this cannot be, this is false. If this is false, then the whole thing will false. So you say, okay, that's conflict, backtrack. Then you basically have to remember what are the variables here, what assignment there you make. Then you flip the closest assignment in your kind of search tree, and then try again, and backtrack. Then you say, okay, now this time I had to flip this other variables and so on. Eventually you find it. So that's a typical set solving. You basically do systematic search, and then when you conflict, you go back and then flip the closest assignment, and then and search again, and then if that fails again, you go back to the next level and then flip. So, okay, so that's that. And then the things that in interest time, to say that we are able to construct LLM to basically follow this kind of train of thought. So basically, you say, hey, LLM, I want you to do train of thought, but your train of thought actually is basically doing search and backtrack. And basically, we do all these encoding and wave function to basically remember when you fail, when you backtrack, what variable you have to flip, what assignment you have to flip. So we show that, and then the next question is, yeah. Oh, the next question is, so that's almost like, yes.
So is this the LLM that's doing the backtracking, or is it like some plugin on top of LLM?
So basically, we using so-called decoder-only LLM, a decoder-only transformer without embedding. So basically, we define what the input, how should the input be represented, and we construct all the transformer layers. Yeah. So basically, it's like we just separate from what we talk about. Meaning that this is really by constructing. We construct the LLM to actually follow the standard set solving process, which is actually not a surprising result, because previously some results say you can use LLM to actually simulate the whole Turing machine. So if you can do that, obviously you can construct LLM to do anything you want. So it's almost like that's besides the point, but you still want to show it. Yes, you can do this. Yes.
Yeah, really interesting work. So I was wondering about the performance of this, because the modern set solvers can.
Yeah, super slow. Yes.
Process, right? So
Yes, super
what's the
slow.
performance?
Yeah. So we have some theoretical result. Basically, say we can do in parallel. Big thing about it, the set solving stuff, right? Because it's this conjunctive normal form, right? So you can actually do some parallelization, so that if any one of them fail, you know it's fail. You basically don't have to go like this. You can do it in parallel. Yeah. So there's some parallelism that you can do.
Okay, so how many classes can you solve at this point?
I look at people, I have 40 something.
Okay.
Yeah. One of the co-authors, he's Vijay Ganesh. He's a set solver kind of expert on the faculty. So I just trust whatever he says. I think he won some award recently, some set solving performance. Yeah. But anyway, but that's like I said, almost a proof by construction, almost not surprising. Like I said, people have proof you can use LLM to actually simulate Turing machine. But then you say, okay, if that's a result, then basically you can construct LLM to do anything you want, except can be super slow. I think the simulating activity machine is super duper slow. It's almost who cares, right? But I think set solving actually pretty good. Actually, the student actually had a compiler that compile any set solving problem into this LM thing, which is makes it much faster. You don't have to like do your manual encoding of the embedding. But anyway, the more interesting results is can you train LLM to do this? Meaning give it enough training data. It will learn how to do set solving. That was the most interesting that you want to know, right? It turns out that yes and no, in a sense that that's the I want to skip this, but this result is that I'll show you this. Basically, if you train it, let's say 3 set, meaning 3 variables, you test on 3 sets, it does very well. Well, in this case, if you say, hey, if it's like 6 set or 6, anywhere from 6 set to 10 sets or 11 set to 15 set, mean in the sense that if let's say if you train LLM on clauses that has 6 variables, okay, it tests on 6 variables set, it does very well. I mean, all these different distributions in the sense that are they all negative in the variable or some mix or whatever, doesn't matter. Fairly accurate. Meaning that if you train on, 6 set, test on 6 set, train on 7 set, test on 7 set, awesome. But if let's say you train on 6 set, 6 anywhere, let's say you train on 6 set, or let's say you train on A set, meaning you only have a variable each clause. You test it on a 16 set, meaning that each clause has 16 variables, goes down. Okay, so that's interesting things are why. Meaning that, hey, isn't that same thing? You're doing this, keep trying, backtracking, whatever, why is it different? Well, mathematically solving 3 sets versus A set, same thing, except of course many more probability that they deal with. Many more, it's just like, to me it's like, what's the conclusion? Is it be able to learn something? Yes, but can you generalize that? We don't know. We don't know why. Quite possibly just the number of variables is too much. That just, if not trained before, maybe not enough ways being trained on this kind of scale, just it could not generalize. Like, I don't know. It's almost like LM is good at giving a sentence with 10 words, but also you tell him to give me a sentence that's 30 words. It's like, okay, at some point lost the context. That's the best I can say.
It's surprising because in the NLP literature,
Yeah.
if you look at the instruction following, then they also report the similar phenomena.
Yeah. So this is not the first time we reported. Sorry.
Can you repeat the question?
Oh, yeah. The question was like in natural language processing, they're saying that they also, different lengths or different.
So in the instruction following, if
Yeah.
you have like a many constraints,
Yeah.
language model can satisfy, let's say, 5 or 6 very well.
Yeah.
But if it goes beyond, then they start to fail.
Yeah. So meaning that the number of constraints is more, then it's starting to fail. I think it gets, unless you train it specifically, it doesn't have not built up the model or the weights to actually figure out which output to give. I mean, I think I've seen other results like in solving math, right? Some of the you ask math question in different ways, it fails. So not totally surprising. So really, just from a pure training point of view, should we conclude that it can learn to reason or not? I think it's a mix, right? Meaning that if you stay within the same distribution, including the number of constraints or number of variables, seems to be doing fine. But beyond that, it's kind of generalized. So.
I found this set problem that you guys tried is very interesting because, like the Yang mentioned, if we have a practical solution that can solve thousands or millions of benefits very well, right?
Yeah.
But theoretically, set problem is the NP complete, right? So
NP complete. Yeah.
So this is a problem that theoretically very challenging, but yet we have a very practical solution.
Yeah, we do. Yeah. So great. So the comment say, set is interesting from a theoretical point of view. The practical aspect may be limited because a lot of people work in set solver for like decades. A lot of very good tools out there. I actually get asked the same thing in the different contexts. My answer is that yes, I know that, but from set, maybe our next target was SMT, right? Because even the SMT solver is there. So what's your point? The point is following. Imagine in the future you say, can LLM to do reasoning? Like what? Let's say reasoning about system safety. problems. I will imagine describe safety problem, and then you somehow decompose into multiple sub-problems. Some of them are set, some of them SMT. The point is that if you think, hey, LLM or large language model can do this, I would say that it should be able to know solving the basic stuff or being able to use the right tool. And then somehow, it's almost like the higher level logic should be a composition of the lower level logic. And if the LLM cannot, we cannot have confidence that LLM can actually do even the lower level logic. How can we have confidence that it can do the higher level logic or composing multiple conclusions into some logical format? You see what I'm saying? So my point is that you can think about, I can decompose your safety question into multiple subclasses. Each of them is a set, but the combining them actually is another set. So it's almost like we need some ability for LLM to actually be able to decompose and compose, and then provide some logical reason, say why this works, right? Now, can we automate SAS solver to go that route? Maybe, but hey, to me, the AI or LLM is trying to automate and scale some of these things. So, all right. So conclude. I mean, I think it's a rundown of a bunch of random stuff, and hopefully, you guys understand that we should not. I think the high-level point is that we should not use AI as a black box. A lot of these safety, privacy questions are super interesting, but also super challenging, right? Because we don't fully understand how LLM works. So for us, I'm a system security guy. To me, is I start with some basic stuff and also try to start to build some kind of sandbox around it. Okay, all right, thank you.
Thank you very much. Thank you very much for your great talk. So do you have a, yeah, there is a question.
Yeah.
Hi, I'm Carleen Maitland. I'm the Associate Dean for Research, and I want to thank everyone for coming. I am interested in impact. So I'm trying to understand. I mean, I see that one way we can ensure privacy is through consumer demand.
Yep.
We can hope that we have benevolent system providers that actually incorporate these technologies.
Yep.
My favorite use case is my Ring doorbell.
Yep.
Because
Totally.
I am the surveiller
Yeah.
unintentionally, right? But at the same time, as somebody walking around my neighborhood, I also want to protect myself. I was thinking like, ooh, those deep fakes, can I deep fake? Like, could I have that
Yeah.
technology to deep fake all the Ring doorbells in my neighborhood? Or policy.
Yep.
What do you think? What's your gut? Where's this going to come from?
Yeah, great. I mean, if you have any good leads, I would love to hear them, because we've been trying the last couple of years to find people adopt our technologies, almost like no, whatever. So I think the two ways. One is surveillance part of thing. I mean, we heard about like your Ring doorbell. I think some of the options they subscribe when you upload the data, they claim to be encrypted, then people find out they're not encrypted. That's again for this kind of adoption, you need a lot of consumers say, no, we want it, right?
So you would go for I think the consumer.
Could be, but the thing is that for public surveillance, I gave up because seriously, the law enforcement agency have all your data. They don't really talk to them about privacy. It's like, no, because nothing you can do about it, right?
Yeah.
But I think even for the authentication thing, we try to, our dream will be, let's say Twitter or X will adopt it, so that there's a real person behind this account, so that you can hold some of the tweet accountable. It's not, you know what I'm saying is like, I don't have to know how the person look like. All I need to know is that, hey, I know the real person behind this account, or the same person can have 10,000 accounts. So you can have some control or some assurance over the information you get. But again, it's almost talking to a wall. It's like people just to me, it's like the biggest lesson I learned is that people don't care enough. And a deeper lesson is that as a technologist, when we design this kind of thing, we think ahead. Don't wait. It's like this. The technology is out there. Then it have been using for a long time, being used for a long time. Now I say, I want to retrofit with privacy. People say, yeah, I'm used to it. Yeah, I can get away. I can get by. So why bother? So that's the kind of thing that's really super important, particularly for students like IST to say, think about how we design technology. They intend it to be used widely. Think through all these possible consequences.
Or we could lobby the Europeans to do it for us.
yeah.
They're already doing it.
Yeah, I mean,
No, they need to go further, right?
yeah, I think European is very interesting. I mean, I listened when I went to Singapore. I asked the same question about privacy. They were like, "What privacy? Everybody has a passport." Meaning they know everybody's
Yeah.
all information.
Oh, yeah.
Yeah, I mean, it's like different countries have completely different view
Oh, yeah.
of privacy. So it's an interesting area. Yeah, thank you.
Any other question? Okay.
Thank you. I thought when you mentioned the input filtering
Yeah.
idea, right,
Yeah.
and then bring the certification to the camera,
Yeah,
that reminds me the ongoing discussion in my community. So I work in the language model and text domain,
yeah, yeah,
and some people argue that detection has the great opportunities and we need to work more.
yeah,
Some people says, okay, we need to work on the pre-generation, so
Right.
more emphasis on the watermarking
yes,
and
yes,
so on, right?
yeah,
So in a sense, your camera idea is similar to the watermarking
Yeah.
in the generation, right?
yeah, yeah,
So the when I look at the discussion in my community, people agree that the watermarking generation idea is really clean and good,
yeah,
but they doubt that practically it's really doable, right? Because a lot of the politics or government issues or
I
the
see.
consensus among the industry
yeah,
agree
Yeah.
to support that, whereas the detection is fairly easy. You just have an algorithm
yeah,
platform adopted and then you can
Yeah.
apply it, right?
yeah, yeah.
So I wonder, how do you think about in this particular
Yeah,
this domain?
yeah, great question. So I think that modern marketing, of course, any technology can be abused, right? You don't want the government to chase whatever thing. Yes, absolutely. My point is that let's say the idea of the camera, hash and sign, put a blockchain. I think those things will be useful when let's say you're a person, you want to make an important announcement. That yes, but maybe day-to-day use, maybe you don't. So my point is that so right now the biggest problem is that some of the authenticity of some really critical things is not even guaranteed. And then you say, okay, well, if I'm Donald Trump, of course, you can call me, I will tell you that's true or not. But what if in a legal dispute, I say, yeah, I saw this person doing this. I said, no, I didn't do it. Then what do you do, right? So my point is there are reasons that those things will be useful. Now, I completely agree that when you have watermark and kind of proof or something, that can be abused too. So that, I don't know, it's a policy thing.
Yeah, I think it's really part of even the fake news, right?
Yeah,
Community agreed that if every newspaper
yeah,
agrees to certify when they generate it,
yeah,
and when they look at the news, they can tell who wrote it,
yeah,
then problem is solved.
yeah.
But nobody
Exactly.
can implement it, right? So
Yeah, exactly. I completely agree. I think that's why Twitter, we actually contacted Twitter, they didn't care. They would say, you can actually make sure there's a person behind this account. Maybe they actually want some kind of fake news. Maybe they actually want some kind of impression that a lot of people are agreeing with something. So, I mean, like I said, some of these things are very beyond what we can understand as technical people. But my point is that we should still engage with them and also think more carefully some of these technology that we put out. Yeah. Thank you.
Okay. Any other question? Oh, okay. Okay.
Thank you for a great talk. Recently in Jensen Huang's talk, I noticed he mentioned a lot of, quote, agent.
Yep.
So I thought, since you mentioned AI a lot of times,
Sure.
so I thought, can you give some comments about, obviously agent is very broad, right? It's more than large language models and so on. So curious, your thought about the issues you talk about security and privacy in that large context.
Yeah, great question. So I think that, thinking about AI as an agent is maybe the first step to think about not as a black box. Like mainly almost break down your application, your workflow into multiple steps, multiple components. Each of them has one agent, maybe a multiple agent to you do a reliability thing like majority vote, want to monitor each other, coordinate with each other. So I think in one sense, give us better way to engineer our system and assess maybe some better guarantee of reliability, but I can push back to say, well, in that case, you make the system so more complicated. So I think that is the right direction. I mean, to go with a agent-based, agentic AI. Basically, like, instead of the one big black box system, you have multiple agents. Like I said, I mean, people talk about digital twin. I mean, that's another hot term that they use, meaning that it's almost like, I mean, it's like, what is Web 3.0? I think Web 3.0 will be bunch of your own digital twin doing things for you. Instead of being controlled by OpenAI or Google, you can have an agent, your digital twin that talk to multiple sources, and maybe different aspects, different digital twin that they don't actually share. At least they don't expose that they're all connected to you, so that nobody can track you. It's something, a lot of things you can do with digital twin on agent. I'm super excited about that. But then on the other hand, a lot of this privacy thing, the ability thing, maybe that's a better way to actually ensure that instead, like I said, the single black box system is hard. But multiple agents have more chance to actually do things right. Yeah.
So I had a question about the reasoning part of the LLM.
Yeah.
So I'm sure you're aware of there's another line of work where they're basically trying to encode these reasoning problems into specifications, and basically then they use like the SMT tools as a tool.
Yeah.
And if you think about this, right, like if you're thinking in terms of like reasoning as a human as well, as soon as the problem gets complex, we're not going to be very good at it.
Yeah.
So what do you think is the way to go to teach the model to reason, or make it learn the tool?
Yeah, great. So I was actually last week I was in Abu Dhabi for a different reason, different meeting. I was like, so there was a keynote by this guy called Edward Lee. I mean, he's a retired professor from Berkeley. He read a bunch of books, and his keynote was about basically most things. Can LLM do reasoning? Basically, first he started by saying everybody should read the book Think Fast and Slow, right, by a famous Nobel Prize winner in economics. Basically saying that, basically it points out that two kinds of reasoning. One is fast, that's based on probability and intuition, based on life experience. Okay, it turns out that a lot of our life decisions, like buying a house, buying anything, that's why it's called it bias regret. You buy things, it's so exciting, and oh man, I should have bought it. Okay, that's a typical thing. That's a human nature thing. You cannot fight it. That's human nature baked into our whatever biological system. Thinking fast, so based on probability and intuition. Turns out a lot of economic decisions based on policymakers. No wonder some people say, let's invade a country. Is it logical reasoning? Bullshit. Of course not. Just thinking fast. I hate a guy who want to attack those countries. Come on. Okay, but that's the world we're dealing with. Okay, that's called fast reasoning, based on probability, intuition, life experience. One is slow reasoning. That's what we computer scientists or mathematicians normally would do, step by step, follow some logical process, right? One cause, here's a theorem, here's a corollary, and here's a whatever, here's an axiom, whatever. Those things. But those are very slow process, very methodical. Most of the time, I got challenged. Hey, do you do that when you decide to come to Penn State? Probably not. Maybe some little bit combination. You know what I'm saying? That so my point is what's reasoning. So his point is that LLM probably is more on the former, fast. Maybe some ability, we show like I said, maybe in some context, constrained enough, maybe can do some slow. But for it to do completely slow, no way, because that's not what language model is supposed to be doing. It's not because we did not build a language model training to do that way. So really the point is that what's reasoning? You have to basically agree. Fast reasoning probably is going to not be how. That's how you've been living your life for a long, long time. And then my pushback is for some very critical applications, super critical applications like what? Autonomous driving. I want it to be super rigorous. Not slow, but super rigorous. You don't want to say, just turn left. Oh, sorry, you should turn right. Damn, you already missed that, right? Or you say, you should stop. There was a stop sign. Really? So for those kind of critical applications, you want to be super rigorous. So I don't have a good answer, but just case by case, right? If you allow me, my favorite joke with AI is that look, if you ask AI system, hey, what happens if I release? Because it's doing your job. Why? Because I learn it. You say, can you explain why it's going to job? It's going to say, hey, because of gravitational theory. Did you figure out? No, because it was on the web. I'll be super impressed if one day, let's say, if that gravitational theory thing is not on the web, you say, oh, I know, I figured it out, here's the formula. I'll be impressed. Then we can all retire. My point is that there's no way AI would get to that point to say, I explained this to you, here's a new formula. I wouldn't say that's possible. Now, of course, I could be wrong, but right now it's based on all the knowledge it learns. Right, so again, maybe it's okay to say, hey, 99% of the time is correct. It knows that when you release it, it's going to drop. Why? Don't know why. You say, why is a problem? You know, I have a friend who's a MD PhD in, he's a neurosurgeon. He tells me that a third of the problems, they know exactly how to solve it from medicine point of view. Another third, they kind of know. They kind of confident they actually know the answer, but they're not, no proof, but they kind of know. Another third, they have no freaking idea. No, nothing. Okay, so my point is that maybe it's okay that the reasoning in the future is, hey, 99.9% of the time is correct. Deal with it. The rest, you know. So anyway.
But I guess for existing knowledge, you still want to encode it. Do you see a good way of combining these two kinds of reasoning? Even just for
yeah, definitely. I think our work now, I am kind of by construction is probably one of the direction that we're trying to move to, right? Basically, for some of the basic building blocks, we want to encode it. So that almost like this, right? You want it to be able to do the basic things right. So they cannot go off too badly, I mean, hopefully. So that even some of the because some of the high level reasoning, like I say, analyzing system safety, you may actually be able to abstract into essentially some still very basic logical problems that you can actually do reasoning there. So that's why I'm trying to say some of the basic simple things. Make sure the LM can do that. So that we are, first of all, it's not complete black box. Second of all, there's some basic ability that we can trust. Yeah.
All right. Yeah. So due to the time, maybe if you don't mind, maybe
Yeah,
we can-
sure.
Yeah,
Yeah.
one more question.
Hello, I've been thinking about the reasoning of the AI recently by myself also. So about having a longer chain or longer length, for example, for the reasoning that the AI is actually losing track, that's also actually, in my opinion, also happening on human kids. Like if you are giving a primary school student that very simple calculation or just 1 + 1, something like that, it may calculate correctly with a very high accuracy.
Yeah.
But if you give it like 1 + 1 + 1 + 1 + 1, something like that, they will lose track.
Yeah.
But the problem is like, is human kids not able to have like slow thinking, or they have to learn, or is our LLM also in that status? Like they are like primary school kids, they are not developed enough to think more like slow thinking.
Yeah.
That kind of perspective.
Yeah, great question. So I think yes, the question is that, you know, basic LLM is making the same mistake as human without proper training. I think that's where at school they teach the kids basic steps. Essentially, think about it, you take a math class, they actually force you to do chain of thoughts. They solve the problem step by step. Let's say 1 + 1 + 1 is okay, well, let's add the two first. And then you're using the 1 + 1 = 2, and then they say 2 + 1 = 3. You see what I'm saying? Basically, a teacher is teaching you chain of thoughts. I mean, I'm almost like, if you go back to your textbook in, let's say, primary school, middle school, you will laugh at the comment, yeah, that's so simple. Are you kidding me? But you spend years and years doing it. Basically forcing you to learn and remember to do chain of thoughts. Right? There's some kids actually become very good at it. You know, those are you who are sitting here, right? Some of them will never get it. They're not here. You know what I'm saying? So really, to your question, yes, I mean, maybe some human nature is that we tend to think fast. But then some of the work that we're doing force us to have to learn the habit of doing slow, because that's the only way to guarantee correct. And so it's really, like I said, the reasoning thing is that, do we have to have a guarantee of correctness? Versus, well, most of the time I'm correct for most of the problems, that's good enough. Really depends. I mean, without offending anybody, I think there's a difference between STEM and humanities. No, don't take it from me. So it's what I'm saying, but if you do STEM, you want to be rigorous. Follow certain rules. Okay, yeah. So really, at the end of the day, is that what do you want large language models to do? Is it automatically replace some of the STEM work versus more on the humanity side. On the humanity side, seems to be doing very well. Yeah. Okay.
All right, then maybe this is the probably end of our his talk, and thank you very much for your attention.
Yeah.
Yeah.
Yeah, thank you, Sam.